I mentioned earlier I wanted to do a robotics project. So the first thing I need to talk about is the motor. And the motor I've chosen is a brushless DC motor, a BLDC. There's two types of brushless motors. There's stepper motors and then there's servo motors, and I have a servo motor. It runs faster and smoother than a stepper. A stepper motor can move in very small increments and has good braking force and very precise, but the servo motor runs smoother and faster, and that's what I'm looking for right now. So let's take a look at it, how it works. BLDC, brushless DC motor, brushless DC current. Okay, so it has basically 3 windings inside. Although you can have more, but right now on this one we have 3 phases, 3 windings, 3 phases. So inside the motor is a controller built inside. Let's put this over here. And that's hooked to these windings. And one goes over here like that. And then inside there's some sensors. They're called Hall effect sensors. There's 3 of them hooked together, and they go to another part of the controller. So basically 6 wires come out, and that's basically what we're concerned with. Everything on here is like kind of deeper theory, and we don't need to know that right now. So basically what I have hooked up on the bench, we have the motor, we got the shaft coming out, and then we got the 6 wires come out. So this motor is a 24 volt, 5,000 RPM motor. We need a 24 volt power supply, which we have on the bench. So we have a plus and a minus going into the motor for our voltage, power. And then we got 4 more come out, 4 more wires. Now, the way this motor is controlled, even though the power is applied to the motor does not turn. The motor needs a square wave input to drive it. Now, it's called pulse width modulation. And that's how you control the speed. So the idea is that's a constant speed waveform right there. And that's about 25% duty cycle. Because the on time is 25% of the off time. That's a 25% duty cycle. A 50% would be equal, where the on time and the off time are the same. So if you have a controller, a computer can send a variable, that's why they call it modulated. So this signal here increases the duty cycle increases, so the RPM of the motor would increase. Also the power. The reason for this is it saves power, because when it's switched on, the power goes directly to the motor and the circuitry doesn't take up much efficiency from the operation. And when it's off, when it's low, it doesn't take hardly any power at all. That's why it works better that way for robotics. So you have the PWM input right here, where the signal goes in. And you have another one for forward and reverse. And you have on, almost forgot that. You have an on-off. And you have a tach. The tach tells you how fast the motor's spinning, and it outputs a waveform, a square wave, where the frequency varies with the RPM. As the RPM goes up, the frequency goes up. As the RPM goes down, the frequency goes down. And that's very important to know, because the computer can read this tach signal and it gets feedback to how fast the motor is actually turning. Even if you're feeding it a signal to go a certain RPM, if there's a big load on the shaft, it may not go as high as without a load. So the tach will tell the computer that, and it can increase the power to compensate for the load on the motor. The computer can also vary the duty cycle of the waveform, and it can accelerate, decelerate, it can go fast, slow, anywhere in between, and it can, in some cases it can brake, as in stop brake. So on the bench, what we have is we have our power supply hooked up just like that, and then this is our PWM, and it comes from MainBrain. MainBrain is going to control it, and it's just, I'm using software to generate a waveform which is called bit banging. So it's sending in a 25% duty cycle at a certain frequency. We can measure that on the bench. And then we have the tach. The tach has to have a pull-up resistor, so MainBrain, actually, there's our MainBrain. It supplies 3.3 volts as a resistor here, and it supplies 3.3 volts. And we'll measure right here, and we'll get a waveform out off the tach. This is the tach. And then we also use MainBrain to turn it on and off. A 0 or a 1. This is on and off. And then we also use MainBrain to forward or reverse. And that's a 0 or a 1. And that's pretty much the circuit on the bench. So let's go take a look at it in real life. Okay, so here we are at the bench. And we have MainBrain hooked up to the motor, and this is the motor. I got a piece of tape on it so you can see the shaft turn. And over here, right here is the power supply, 24 volts. We got MainBrain hooked up with that little board here. And here's our scope. So we got a waveform on here. This is a 25% duty cycle waveform, and that's coming out of MainBrain. And this is the tax signal here. Channel 2 is the tax signal. We don't have nothing going yet, so we'll go over here to MainBrain and go to I/O, and we'll turn the motor on. So here you go, there's the motor turning, and there's our tax signal up at the top. And then if we want to reverse the motor, we'll just hit right here, and we can turn it off. Alright.